Welcome to another deep dive. Today, we're going deep into something pretty fascinating. We're talking about Google's Maglev. It's the system that, keeps Google services running smoothly for millions and millions of users. We'll be looking at excerpts from a research paper written by the engineers at Google who actually built this thing. And trust me, this isn't some dry technical read. It's actually a really interesting story about how Google keeps its services humming, even with the crazy volume of traffic.
Yeah, it's a pretty unique challenge. I mean, Google's handling millions of search queries every second, right,
Yeah.
across hundreds of services and globally. It's a scale that most people just can't even imagine. And that's precisely why network load balancing is so critical to their entire operation.
Right. So before we get into maglev specifically, could you just remind us what network load balancing actually is? I feel like it's one of those terms that gets thrown around a lot, but maybe not everyone fully understands it.
Yeah, absolutely. So network load balancing is all about making sure that no single server gets slammed with too much traffic. It's about making sure that the workload is distributed efficiently across all of the available servers. You can think of it like a busy restaurant, right? They need a host to seat people at different tables to make sure that that there aren't any crazy wait times and things don't descend into chaos. Network load balancing is basically the internet's version of that host. It just keeps things running smoothly.
Gotcha. Okay, that makes a lot of sense. So then what was wrong with the traditional way of doing things? Like, why did Google have to reinvent the wheel here and come up with something entirely new?
Yeah, so traditional load balancers, they were typically hardware based and they worked okay up to a point, but with Google's just insane growth, they eventually hit their limits. It's like trying to manage that busy restaurant we talked about, but with a seating chart that's carved in stone, right? You need something a lot more flexible, something that can adapt to change.
So they basically looked at their massive server infrastructure and just said, there has to be a better way to do this.
That's exactly it. And that's how Maglev was born. They created a software-based load balancer that actually runs on the same servers that are handling all the traffic. And this new approach comes with a whole bunch of advantages. One is scalability. So you can very easily add servers or remove servers as needed, to adjust the capacity of the system. Second is availability. Maglev uses what's called N+1 redundancy, which makes it much more resilient than those older traditional like 1+1 hardware setups. And then third is flexibility. Because Maglev is software, it means that the engineers at Google have full control over it, right? They can tweak it, optimize it, add new features. It's really quite elegant.
So no more stone tablets for the seating chart. Now they've got like a dynamic whiteboard.
You got it. Exactly. And, an added bonus is that using existing infrastructure is just way more cost effective.
Makes sense. Okay, so maglev is Google's, their solution to this really, really difficult problem. It's scalable, it's resilient, it's flexible, and it's cost effective. But how does it actually work? Can you walk us through the journey of a single user request, like a search query, for example?
Sure. So first, that search query, that request is going to hit a router. That's like the entry point to Google's network, right?
Hmm.
And here's where something called ECMP comes into play. ECMP stands for Equal Cost Multipath, and the router uses this to distribute traffic across multiple maglev machines. So it's like intelligent traffic management, right? You're making sure that all lanes are being used.
So the router is kind of like a really, really savvy traffic cop, right? It's directing cars to different routes to make sure that there's no congestion.
Yep, exactly. And then once the request gets to a maglev machine, there's a component there called the forwarder. And this is really, this is where the magic happens. The forwarder is going to analyze the incoming request and decide which server is the best one to handle it. And it does this using some really clever techniques.
So the forwarder is like the host in our restaurant analogy,
Yeah.
deciding which table's the best one for a group of guests.
Exactly. And once the server is chosen, the request gets encapsulated and sent on its way. But here's the really cool part. The response from that server actually bypasses Maglev entirely. It goes directly back to the user. It's a mechanism called direct server return. So basically, Maglev puts all of its energy and effort into managing the incoming traffic.
Interesting. That's efficient, right? It's like the host just pointing you towards your table and then, trusting that you'll find your way out on your own. Now, I know from the paper that Google also uses much larger, more complex clusters. So how does Maglev handle that?
For those really massive clusters, they actually use additional hardware called encapsulators. And that's primarily just to deal with the sheer volume of data that they're processing. But even at that scale, the fundamental principles of Maglev remain the same.
Okay, so we've got the traffic flowing nicely, thanks to ECMP and the forwarder.
Hmm.
But how does Maglev make sure that all the requests from the same user, like all the parts of loading a web page, how do they all end up on the same server?
Right, so that's where things get a little more interesting. Maglev uses two key techniques. One is called connection tracking, and the other one is called consistent hashing. And these work together to make sure that the user has a completely seamless experience.
Okay, I'm all ears. Let's unpack those techniques.
Okay.
Yeah, I'm all ears. Let's unpack those techniques. All right, so connection tracking. Basically, you can think of it like Maglow's short-term memory, right? It remembers where each connection, like when you're loading a web page, it remembers where that connection has been assigned. So it's kind of like a mental note saying, okay, this user's request is going to go to server X. So then when a new request comes in from that same connection, Maglev doesn't have to start from scratch. It just knows exactly where to send it.
Gotcha. So connection tracking makes sure that things stay smooth as long as nothing changes. But in a system like Google's, things are constantly changing.
Oh, absolutely, yeah. Servers can go offline, new ones come online, there are upgrades happening all the time. And that's really where consistent hashing comes into play. It's kind of like the backup plan, right? It makes sure that even when things are changing, those user requests, they still end up at the right server.
Okay, backup plan. I like it. But how does it actually work? We've all heard of consistent hashing, but honestly, it sounds a bit like magic to me.
Yeah, it's pretty clever, but it's not magic. The basic idea is to create this big lookup table, right? And each server is assigned a portion of the entries in that table. You can think of it like slicing a pie, you know?
Yeah.
And each server gets a slice of that pie. And then when a request comes in, Maglev uses a hash function. And that basically figures out where in the pie that request falls, which slice, and that determines which server is going to handle it.
Okay, slicing a pie. I can visualize that. So why is this consistent? Like, what makes it so special?
So the really cool thing about consistent hashing is how it handles change, right? Let's say a server goes offline. In a traditional system, you might have to remap everything, right? But with consistent hashing, only the slice of the pie that belonged to that offline server is affected. Everything else just stays the same.
Ah, so instead of like rebaking the entire pie every time one slice goes bad,
Yeah.
you're just replacing that one piece. Much more efficient.
Precisely. Now, there are actually many different ways to implement consistent hashing, but what really sets Maglev apart is it's their focus on even load distribution, right? So Google really wanted to make sure that no single server was getting overloaded, even if that meant, maybe sacrificing a little bit of consistency in some really, really rare cases.
So they basically said, we're going to prioritize balance above all else.
Hmm.
Was that, was that a tough choice? Were there any trade-offs?
Well, yeah. I mean, every design decision has trade-offs, right? In Maglev's case, if they had prioritized perfect consistency, it might have meant that, that some servers were getting hit a lot harder than others, even with the pie sliced very carefully. And for a company like Google, where, even a tiny performance dip can impact millions of users, that was just not acceptable.
Right. So even load distribution was the winning strategy in the end. Makes sense, given the scale that they're operating at. Now, I know the paper also talked about, some of the operational experiences that Google's had with Maglev. What were some of the big lessons that they learned over the years?
Yeah, so one key evolution was in how they handle server failures. That failover process that we talked about. Initially, they were using what's called an active-passive setup. So you can think of it like having two hosts at that restaurant, right? One is actively seating guests, and the other one is just kind of standing by, just in case.
Okay, so like a backup host, always ready to step in if needed. Seems a little bit wasteful, though, right? Like having half your capacity just sitting idle.
Yeah, exactly. It is a little inefficient. So they eventually moved to an ECMP model where all of the Maglev machines are actively handling traffic. Now, that's a lot more efficient, but it also means that the system needs to be incredibly robust, to handle any failures without skipping a beat.
And that's really where that resilient hashing algorithm comes in, right? Even if one of those hosts steps away for a minute, the guests keep flowing smoothly.
Exactly. Another interesting lesson they learned was around packet processing. So initially, Maglev relied on the Linux kernel to handle some of that. And, well, that added a little bit of overhead. So they eventually developed a way to actually bypass the kernel entirely. And that really dramatically boosted the performance.
So they found a way to, like, streamline the whole process,
Yeah.
cut out any unnecessary steps. And I imagine at Google scale, even small optimizations can make a huge difference, right?
Absolutely. Oh, and they also had a really fascinating challenge with something called VIP matching. So every Google service, it has a virtual IP address, a VIP, and that basically acts as the entry point for that service. But these VIPs, they need to be mapped to the correct servers and different data centers all over the world, right? And sometimes traffic needs to be redirected very, very quickly, like if a data center has any problems.
So it's like having a central directory that knows the address of every restaurant in this massive Google network. And then if one restaurant is closed, you need to very quickly tell everyone where else to go.
A perfect analogy.
Yeah.
So they came up with this really clever system using prefixes and suffixes, and that allows Maglev to seamlessly redirect traffic, even to clusters that it's never seen before.
Okay. That's some really smart engineering. What about those fragmented packets that we talked about earlier? The paper mentioned that those were they were a bit of a headache for Maglev's consistent hashing.
Yeah, so fragmented packets, they're tricky because a fragment might not contain all of the information that's needed for consistent hashing to actually do its job, right? So they had to come up with a way to make absolutely sure that all of the fragments from a single request end up at the same Maglev machine.
Otherwise, you'd have pieces of a web page scattered all over the place. Total disaster.
Exactly. So what they did was they actually redirect the fragments, and they use this temporary table to store some information. And then they rely on the receiving server to put all the pieces back together in the correct order.
So it's like carefully labeling all the pieces of a puzzle before you send them out, so that you can make sure that they're going to be reassembled into the complete picture on the other end. That's really clever. But with a system this complex, how does Google monitor all of this? Like, how do they know if something is going wrong?
Right. So that's where their monitoring system comes in. They use a combination of they use what's called black box monitoring and white box monitoring. So black box monitoring is kind of like having secret shoppers, right? Testing the services from the outside. And then white box monitoring is Maglev itself. It's reporting on its own internal health.
So they're getting both the customer's perspective and the internal view. Good way to catch any problems early.
And if something does go wrong, they have this really, really powerful tool that they call Packet Tracer. And this allows them to literally track a single packet's journey through the entire system.
Wow. So it's like a tiny little GPS tracker attached to each request. Talk about visibility.
Yeah. Packet Tracer is incredibly valuable when you're trying to debug something in such a complex distributed environment. You can pinpoint exactly where a bottleneck or an error is happening.
So after this deep dive into Maglev, I'm really curious, how does it actually perform in the real world? Like, does it actually live up to the hype? So after this deep dive into Maglev, I'm really curious, how does it actually perform in the real world? Like, does it actually live up to the hype?
Well, Google's own tests have shown some really impressive results. Maglev is excellent at distributing traffic evenly across, hundreds of servers, just as they intended. And they've achieved incredibly high throughput on individual machines thanks to that kernel bypass.
So the servers are humming along, the traffic is flowing smoothly. Sounds like everything's running like a well-oiled machine.
And the best part is that their consistent hashing algorithm has proven incredibly robust. In real-world conditions, it can adapt to servers going offline, new ones coming online, all while keeping that traffic balanced. It's really the adaptability that makes Maglev so impressive.
Okay, so we've covered a lot of ground here. We've seen how Maglev tackles this, this immense challenge of network load balancing at Google scale.
Mm-hmm.
And it's really the reason why services like Search and Gmail and YouTube, they all remain so responsive and reliable for millions, even billions of users around the world. It's just a fantastic example of how software can be used to address real-world problems in really innovative ways.
What I find most fascinating is that, a system of this complexity can be made understandable. By breaking it down into those core components and, with a few analogies here and there, we can really appreciate the ingenuity behind Maglev's design.
And it leaves us with a thought-provoking question, right? The internet is growing exponentially. More devices are coming online. There's more data being generated every second. What does the future hold for load balancing? What new challenges and innovations might we see?
Yeah. Maglev is a testament to the talent of those engineers at Google, but it's certainly not the final word. As technology evolves, so too will the systems that keep the internet running smoothly. That demand for speed and efficiency and reliability, that's only going to continue to grow.
Well, on that note, we'll leave you to ponder the future of network load balancing. We hope you enjoyed this deep dive into Google's Maglev. It's a pretty incredible system. And, understanding its inner workings gives us all a glimpse into that complex machinery that powers our digital world.
And if you have any questions or insights, feel free to share them with us. Until next time, keep exploring, keep learning, and keep diving deep into the technologies that shape our lives.